Hi guys, welcome to my lesson on bisectors of triangles. In this lesson and in the next lesson, we're going to learn something really cool about triangles. And that is that unlike circles, which have one center, triangles have four different centers that we're going to study. And these four different centers are created when we draw four different types of lines that we can draw within triangles. The first two that we're going to talk about in this lesson are bisectors of triangles. We're going to talk about perpendicular bisectors and angle bisectors. Let's take a look at our new vocabulary. So a perpendicular bisector is a line that bisects another line segment and is also perpendicular to that segment. So whereas I could say this line segment AB, okay, perhaps I could draw, if that is the midpoint of AB, perhaps I could draw some line that just goes through here like this. We'll call it line L. It bisects AB, okay, but it's not a perpendicular bisector. I will draw another line that comes through here like this. I'll call this line M, and if M both bisects AB and happens to do so at a right angle, and we call that a perpendicular bisector. And there's some really significant things that we know when we're dealing with perpendicular bisectors that we'll talk about in the next couple slides. Another new term is concurrent lines. Okay, this is a really interesting phenomenon that occurs with our four different types of centers that I referenced in our triangles. It happens when three or more lines intersect at a common point. Okay, now if you pick any two lines that are not parallel, there's no surprise that they are going to cross at some point. Okay, they're going to intersect. But what are the odds that if I pick a third random line, that it is going to cross these two at exactly the same point? When that happens, it's kind of interesting. It's an interesting phenomenon. And that's why we call these three lines concurrent lines. It can be three or more as long as they intersect at a common point. And that common point, as you might imagine, is what we call the point of concurrency. Okay, so that is a significant point where concurrent lines intersect. Okay, and we're going to talk about two of these types of points of concurrency in triangles in this lesson. The first one is circumcenter. Okay, and the circumcenter it's the point of concurrency where if you draw within a triangle three perpendicular bisectors, they are going to converge at that point of concurrency that we call the circumcenter. And this is a very significant and useful point to find in a triangle because it closely relates triangles and circles, as we'll see later on in chapter 10. Another point of concurrency is our incenter, and this is what happens when we draw, instead of three perpendicular bisectors, we draw the three angle bisectors in a triangle, and they are all going to meet at the incenter. We're going to talk a little bit more about incenter later and what its significance is. Let's first take a look at perpendicular bisectors. So here are our perpendicular bisector theorems. Our first one, 5.1. Perpendicular bisector theorem tells us that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. What does that mean? Okay, so you'll notice here that line CD is a perpendicular bisector of segment AB. Not only does it bisect segment AB, but it does so at a right angle. So it's a perpendicular bisector. Any point on line CD, whether it's C or D, or I could extend this down to some point E, or up further to some point F, every one of these points is equidistant from the endpoints of AB. In other words, it's the same distance. C is the same distance from A as it is from B. Likewise, F is the same distance from A as it is from B. And you might be thinking, well, that just looks like an isosceles triangle. That looks like what we learned about isosceles triangles when they're doing coordinate proofs and whatnot. You're absolutely right. That's what we're dealing with. Okay, the converse of that perpendicular bisector theorem is that if you know a point is equidistant from the endpoints of a segment, and conversely, it must be on the perpendicular bisector of the segment. So if you told me that E was the same distance from A as it is from B, I could tell you that it must be on a line that perpendicularly bisects segment AB. Same thing with C. If you told me that C was the same distance from A as it is from B, I could tell you that it must be on the perpendicular bisector. Okay, with those theorems in mind, here, could we find BC? Okay, first thing I notice is that CD, line CD, bisects segment AB, and it intersects it at a right angle. Therefore, it's a perpendicular bisector. That means point C is on the perpendicular bisector of AB, and if that's true, it's the same distance from A as it is from B, and therefore I want to go ahead and mark that, and that would make the measure of the length of segment BC 8.5. Okay, here could we find XY? Now again, I notice this line WY is perpendicular to XE. I don't yet know that it's a perpendicular bisector because I don't know XY and YZ. In fact, XY is what we're looking for. But they did tell us that these segments are congruent. And that means that W is the same distance from X as it is from Z. And therefore I can conclude W must be on the perpendicular bisector of XZ. And if WY is perpendicular to XZ, then this must in fact be the perpendicular bisector. I can conclude that XY must be congruent to YZ, and XY therefore must be 6. All right, here could we find PQ? Okay, so you'll notice that we've got QS, which is perpendicular to segment PR, and it also bisects PR. We can see right there. That means QS must be a perpendicular bisector. Q is a point on the perpendicular bisector, so it must be the same distance from P as it is from R, and therefore 3x plus 1 must equal 5x minus 3. Can we go ahead and solve this for x? We'll subtract 3x from both sides. If you want, we can add 3 to both sides at the same time, and this will clean up nicely. We get 4 equals 2x divided by 2. We get 2 equals x. Okay, but they want to know PQ, so I got to remember to plug it back in. 3 times 2 plus 1 gives me 7. Good. All right, here's the first of our 4 points of concurrency that we're going to study in triangles, circumcenter. And circumcenter theorem tells us that the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So if you were looking for a point that is exactly the same distance from A as it is from C as it is from B, you'd be looking for the circumcenter. So to do that, you're going to have to draw the 3 perpendicular bisectors in that triangle. You're going to take the midpoint of this side BC and construct a line at a right angle to it. And you can extend that out. So there is one perpendicular bisector. You can extend it out in both directions. We can do the same thing on side AB. We can find this point D, which is the midpoint of AB, and then construct a perpendicular line through it. And it's going to intersect with our other perpendicular bisector at this point P, which is our circumcenter. We can do the same thing for side AC. Find the midpoint, construct a perpendicular line, and you'll find it's going to intersect at exactly the same place. And that's what makes this neat, is that third line happens to intersect at the exact same point is pretty unique. Now, how do we know this is true? How do we know that this point is equidistant from all of the vertices of the triangle? Well, let's first start with our point F here, this midpoint. We did establish this at the midpoint of BC, and we constructed a perpendicular bisector. Therefore, we know P is on the perpendicular bisector of BC. It must be the same distance from B as it is from C. Okay, now let's shift over here, and we established D at the midpoint of this side. We constructed a perpendicular bisector, and that tells us that P is the same distance from B as it is from A, and therefore this segment must also be congruent. So if these three segments are congruent, that means point P is the same distance from A as it is from B as it is from C. All right, let's try some problems with circumcenter. Okay, our first problem with circumcenter, excuse me, is it's actually an interesting thought experiment about circumcenter and what it represents. We've got a garden, a triangular shaped garden is shown. Can a fountain be placed at the circumcenter and still be inside the garden? Okay, now you're probably thinking, Mr. Rogers, you're telling us about these centers of triangles. Of course they're going to be inside the triangles. How could something be the center of something and not be inside it? Well, you're going to find out here that not all of these centers are always inside the triangles because of what they represent. Okay, so let's find our circumcenter and then just see, is it going to be inside or outside? And there's a couple different ways you can do this. Let's just construct two perpendicular bisectors. We can construct all three of them if we want. There's two ways to do this. We can do it with our compass, like we learned in chapter 3, or you could do it by finding the midpoint of a side and then using a protractor to establish a 90-degree angle. I'll do one here with a compass, and then we'll do one with a protractor. So you can see here, this is the perpendicular bisector of side XY. Let's give that 2 slashes, okay? Let's construct the other perpendicular bisectors. If you're going to do it with a protractor, you're going to need a ruler as well, because you've got to measure and find the midpoint. I find that this side is 4 inches long, so the midpoint will be at 2. Okay, and then I'm going to go ahead and establish a 90-degree. I'm going to have to extend this out so I can see, line up my 0 on my scale. Okay, I'm going to go ahead and establish a 90-degree angle here. And you can see that this perpendicular bisector is going to go just like this. So you can do this either way. You can do it with a compass. I kind of like the compass. It's kind of slick. But if you've got a protractor and a ruler, you can do the same thing. So that's going to be true. And already we can see this is where our circumcenter is. Okay. If you want to go ahead and establish this other one, here we have the side is also about 4 inches, so midpoint's going to be at 2 inches. And I'm going to extend out this side so I can get my 0 on my scale. And I'm going to put a 90-degree mark right there. Connect these two. And what do you know? All three of these perpendicular bisectors converge at the same point that we call the circumcenter. Okay, this point is the same distance from X as it is from Z as it is from Y. And is our circumcenter always inside the triangle? Clearly it's not. Under what circumstances is our circumcenter going to be inside the triangle versus outside? Okay, and the key is in this angle right here. Okay, hopefully you notice that this triangle is obtuse, and if you have an obtuse triangle, your circumcenter is going to lie outside the triangle. If you have an acute triangle, your circumcenter is going to lie inside the triangle. What do you think is going to happen if you have a right triangle, a triangle that is neither acute nor obtuse? Where is your circumcenter going to lie? Well, if you draw those perpendicular bisectors for each of the sides, you are going to find that they all converge at a point that sits exactly on the hypotenuse. Okay? So then where is our circumcenter going to be for a triangle like this? A triangle used to rack pool balls is shown, and it looks a little bit out of scale, but I think normally a triangle used to rack pool balls or billiard balls is an equilateral triangle, which is a type of an acute triangle. So hopefully you recognize that your circumcenter is going to be somewhere inside. If you want, you can draw those perpendicular bisectors and check it out, but you will find that your circumcenter for all acute triangles is going to be inside the triangle. Okay, now we're going to talk about angle bisectors. Okay, so an angle bisector, remember, if we bisect an angle, if you've got some angle here, let's call it ABC, and you draw another ray, okay, you draw some other ray, maybe it's BD, let's call it BD. And if BD is an angle bisector, then it's going to cut this larger angle into two congruent angles. That's how you're going to recognize when you're dealing with an angle bisector. And in a triangle, we have three angles, so we can draw three angle bisectors. And here's what's important to know about angle bisectors. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle. Now, what does that mean? If I am anywhere on this angle bisector, I am the same distance from ray BD as I am from ray BE. These are the sides of the angle, right? Now, how do we find the distance from some point here to a ray? Well, it's the same way we find the distance from a point to a line, which we learned about in chapter 3. It's going to be the perpendicular distance. So from any one of these points, if you want to know how far you are from this ray, you're going to go at a right angle, in here, at a right angle. And if this is true, then this point F will be the same distance from this ray as it is from this ray, meaning that FD will be congruent to FE. So this is something you can conclude if you're dealing with an angle bisector. Okay, the converse of that is that if a point in the interior of an angle, remember the interior we're talking about, anywhere in here, this is our interior, as opposed to our exterior out here. If you're a point in the interior of an angle and you happen to be equidistant from the sides of the angle, then you know that point is on the angle bisector. So in this case, if they told us that F is the same distance from D as it is from E, that tells us FD and FE are congruent. That means F must be lying on an angle bisector. I could conclude that this ray must be an angle bisector if all I was given was this information right here, telling me that these perpendicular segments are congruent. All right, let's try some examples with this. Here, could we find segment DB? Okay, well, the first thing I notice is these two symbols here tell me that AD is an angle bisector. AD is bisecting angle BAC. And therefore, if point D is on the angle bisector, then these segments must be congruent. And that would mean that BD must be 5 units. Okay, here could we find the measure of angle WYZ. WYZ. So this guy in here is what we're after. Okay. Well, they're telling me that WZ and WX are congruent. Okay, and because they're both perpendicular to the sides of the angle, I can conclude that W is the same distance from this side of this angle as it is from that side. And therefore, I can conclude that YW must be an angle bisector. And if that's true, then this is true. And if that angle is 28, then this angle is 28 degrees as well. Okay, here could we find QS? Again, I'm noticing these symbols here telling me that these angles are congruent. That tells me PS is an angle bisector. It's bisecting angle QPR. And if that's the case, then SQ must be congruent to SR. If that's true, then 4x minus 1 must equal 3x plus 2. Can we solve that for x? Let's go ahead and subtract 3x from both sides while we add 1 to both sides. And we're going to get x equals 3. Okay. That's not what they wanted though, right? They want to know QS. Can we plug it back in? 4 times 3 is 12 minus 1 is 11. Good. Okay, one more example here. Could we find the measure of angle HFI? Okay, well, HG and HI are congruent and they're both perpendicular to the sides of the angle. So H is the same distance from this side of the angle as it is from that side of the angle, H must be on the angle bisector. This must be an angle bisector. These angles must be congruent. And if this angle is 30, then this angle must be 30 as well. Okay, one more example like this. Find the length of segment UV. And notice here, these angles are congruent. That means TV is an angle bisector. That means these segments must be congruent to one another. Therefore, 3x minus 2 must equal 4x minus 9. And we can go ahead and solve that for x. Subtract 3x from both sides. Add 9 to both sides. And I think we're going to get 7 equals x. We want the length of UV, so let's plug 7 in here. 3 times 7 is 21, minus 2 gives us 19. Good. Okay, just like perpendicular bisectors converging at the circumcenter, angle bisectors converge at a special point of concurrency as well, known as the incenter. Okay, so if we draw all three of the angle bisectors in a triangle, they're going to converge at the same point. We'll call this point P here. This is the incenter, and what's cool about the incenter is it is equidistant, not from the vertices. It's equidistant from all three sides of the triangle. Okay, and that should make sense because any point on this angle bisector is equidistant from both of these sides. Same thing here, and when they all come together, they're going to be at a point that is exact same distance from side AB as it is from side AC, as it is from side BC. In other words, these three segments that you can draw to the sides of the triangle are going to be congruent to one another. This is something that would be practical if you had it working with a triangular piece of material and you needed to drill a hole and you needed to provide the same amount of tear out resistance or strength on each side, and you wanted it to be the same distance from all three of those sides. You'd be looking for the incenter. To do that, you would draw all three of the angle bisectors. All right, let's try some examples. Okay, they want us to find ST if S is the incenter of triangle MNP. Okay, if S is the incenter, then there's some things that I know. And I know you're probably looking at this and saying, that doesn't look to scale, Mr. Rogers. Yeah, sometimes that happens. Okay, there's a lot of things that are true here, though. If that's the incenter, well, then these angles are congruent. These two angles are congruent to each other. These two angles are congruent to one another. And when we get to this incenter, we know that this point is equidistant from the sides of the triangle. Therefore, this must be congruent to that, must be congruent to that. Okay, and they want us to find ST. Okay, so what's cool here is if I can find SU or SR, I also know ST because they're all going to be congruent to one another. Notice if I was just working over here, I don't have enough information to figure out ST. I don't know anything about the size of these segments. But look at this triangle over here, USP. I've got 8, 10, and let's go ahead and call this X. Because if I knew X, well, ST is X. That's what we're after, right? And what's cool here is that when we draw this segment that represents the distance to the side of the triangle, when we're talking distance from point to a line, we're talking about the perpendicular distance, we end up with a right angle. And so we've got a right triangle here we can work with. And Pythagoras can give us some ideas here of what to do, right? X squared plus 8 squared should equal 100 squared, okay? And if you clean this up, you might even recognize this as a Pythagorean triple. X squared plus 64 equals, excuse me, I wrote 100 squared. I was getting ahead of myself. 10 squared is 100. You might recognize this as a Pythagorean triple because when we go to solve this, we get x squared equals 36. And when we take the square root of both sides, we get x equals 6. Okay, that's a 6, 8, 10 triangle. So how long is ST? Well, if this is 6, then ST is also 6, and SR is also 6, in spite of the aforementioned scale issue. Okay, here's a good problem. They want us to find the measure of angle SPU. I'm going to go ahead and highlight that SPU, this angle down here. That's what we want. If S is the incenter of triangle MNP, okay, so if this is the incenter, that means these guys are all angle bisectors. That means this angle is congruent to that angle. This angle is congruent to this angle. This angle is congruent to this angle, okay? So how does that help me find angle S? It doesn't look like I know anything about this angle. I don't know angle NPM. Otherwise, I just take half of it. But let's fill in what we do know. If these angles are congruent, and this one's 33, well, so is this guy. And if these angles are congruent, and this one's 28, well, so is this guy. And if these angles are congruent, and I don't know either one of them, and if one of them is X, so is the other one. Okay. Hopefully you see an equation here, triangle sum theorem, X plus 28 plus 28 plus 33 plus 33 should equal 180. If you add all of these angles up, you should get 180 degrees. So we get 2x plus 56 plus 66 equals 180. Okay, and when we combine like terms again here, we get 2x plus 122 equals 180. Okay, and we will subtract 122 from both sides. We get 2x equals 58. I'm going to divide both sides by 2, and I get x equals 29. So this is 29 degrees, and this is 29 degrees. Good. All right, one last problem for this lesson here. They want us to find the length of segment GF if D is the incenter of triangle ACF. So we're looking for GF. We're going to find the length of this segment out here. This is slightly different, but we can do this. If D is the incenter, that means it's the same distance from this side of the triangle as it is from this side of the triangle as it is from this side of the triangle, okay? And in this particular case, we didn't even really need to know that because we can work entirely within this right triangle. But if they had given us 5, I'll have to rewrite this problem. That would be so much more interesting if this was 5 and this was not given. We could conclude that this is 5, and now what we're after is x, okay? So Pythagoras can help us again here because 5 squared plus x squared should equal our hypotenuse squared, which is 13 squared. Okay, you might recognize this as a Pythagorean triple. This is a really important one. You'll see it a lot if you do roofing. So you get 25 plus x squared equals 13 squared is 169. We'll subtract 25 from both sides. You're going to get x squared equals 144. That's gross. We can take the square root of both sides, and we get x equals 12. Excellent. Okay, guys, I hope you found this lesson helpful. Don't forget to tune into the next lesson. This lesson and the next lesson really build an interesting understanding of triangles and these 4 different types of centers that we're going to learn about. Really fascinating stuff. Hope you found it interesting and helpful, and good luck on the homework.